Now, today again I am dealing with the multivariable constraint optimization problem. I explained one of the methodology, that was the direct method, and to solve the constraint nonlinear programming problem I told you there are several methods available. Now, one of that Cayley's cutting plane method, that was the sequential linear programming method we have solved. Now, today I will tell you the method of feasible direction, that is Zaudensik method to solve the constraint nonlinear programming problem. Now, let me tell you the basic philosophy of this feasible direction method first. Now, if we have constraints like this G1, G2, G3, and this is less than equal to, that is why this is the feasible space for us, and this is the level curve of the objective function. Then this is the optimal solution. This graph already we have shown you before. Now, at this point you see this direction is the grad of G2 direction. This, let me do the directions with different color, then it will be understandable. And this direction, that should be the, this must be grad of G1, that is the normal. If I draw a tangent here at this point, this is the normal to that tangent is the gradient direction at this point of G1. Okay. And at this point, if I consider the grad f, this is the grad f direction. That is why the opposite, this one is the minus grad f direction. All right. Now, from here, this is the feasible direction. From this point, if I move this way, this is the feasible direction. That is why if I consider this is one of the direction as S, okay, then we can say that S is making acute angle with this and S is making obtuse angle with grad of G1 or G2. Okay. That is why you had the relation that grad f dot S minus grad f, and you had the relation grad G I dot S. This is the feasible direction if this is greater than 0, making the acute angle, and for the other thing S is the feasible direction if this is less than 0. All right. But on the other way, if I tell you in the ascent direction grad of f is less than 0, but grad of f dot S is less than 0 for the descent direction, it is also true. Okay. The Zaudensik method of feasible direction based on this fact. From any point, we will find out what is the descent direction for the minimization problem and what is the ascent direction for the maximization problem, as well as we see that what is the feasible direction from this point. Okay. This is the direction is happening for the feasible direction. This is the direction for the ascent direction. All right. Instead of this point, if I consider a point here, what we can see? This is the minus grad f direction. All right. And what about grad G1? This is the grad G1 direction. This is the grad G2 direction. That is why what would be the feasible direction for the minimization problem from here? I will move here through this from any path from this point I have to reach to this point. That is why the method should be such that it should guide me in such a way that if I start my journey from here, it should guide me in such a way I will end up here, alright. If I start from here, I should end up here with the shortest path I have to come. That is why the Zaudensik method of feasible direction, it has been said that you proceed from a point, you proceed to that direction where you are getting the direction as is feasible as well as descent. Clear? From here, if this is the guess point of my optimal solution, then you see I cannot move further within the feasible space with these two conditions. But if I start from here, I can do it. If the problem is of maximization type, the optimal solution cannot be here. If this is the level curve of the objective function, then optimal solution must be somewhere here. Okay? That is why the method should guide me in such a way that if this point is my starting point of my journey, for maximization problem, I should move through the ascent direction as well as I will go through the feasible direction. That is the basis of the Zaudensik method of feasible direction. Now, if we consider a minimization problem of type minimization of f(x) subject to g(x) less than is equal to 0, and we can see that descent direction, since this is the minimization problem, then st grad f less than 0, that is the descent direction, and st grad g less than 0 is the feasible direction. Direction means what? Direction means, if you remember that I was saying that if I start my journey from xk point, then I will move to the point xk plus 1. How? Xk plus 1 would be xk plus lambda k sk, while lambda k is the step length and sk is the direction of the corresponding point. Okay? We can have infinite number of directions, but if we consider a single component of n dimensional space, this direction can be only in the right or in the left. Okay? That way. And the Zaudensik said that if any direction is descent as well as feasible, that must be usable direction for the minimization problem. And for the maximization problem, if the direction is ascent as well as feasible, that is the usable direction. Okay? That is the term given by Zaudensik, that we will move through the usable direction. We won't say that we will move through the descent direction or ascent direction. We will say that we will move through the usable direction. Okay? That is why we will move from xk to xk plus 1 in such a way the direction must be usable in nature. That is the basic philosophy of Zaudensik method. Now, this method is again an iterative process. You must be understanding that we will start from a guess point, we will move through the next point, we will reach to the next point through the usable direction, again we will go to the next point through the usable direction. How long we will do? As long as we can, we will remain within the feasible space. Once we feel that we are out of the feasible space, we will stop our journey and we will declare that could be the optimal solution. That is the beauty of this methodology. And another thing is that all the points are within the feasible space. That is why we will do in such a way that we have to remain in the feasible space. How to define the feasible space? Once we have the constraint set, defining feasible space is not a problem for us, because we will say that from this point to this point you move to such a point where the point must be within the feasible space, the point must be in the usable direction. These are the two things we will mention in the methodology. That is the beauty of this feasible direction method. Okay? And for explaining more about it, I am just giving one example what does it mean about the descent direction and that is the feasible direction. This is the problem for us. You must be realizing descent direction corresponds to the objective function and feasible direction refers to the constraint function. That is why we will deal both the functions together now. We have the function f as x1 square plus x2 square, and we will have the function g, that is the constraint function, as minus x1 minus x2 minus 4. We are making it plus 4. We are making it less than is equal to 0. If we do so, then what is your grad f? Grad f would be 2x1 2x2 transpose, because that is a column vector. Grad g would be is equal to minus 1 minus 1, that is again a column vector, that is why we are putting it as a transpose. Let me take one point, that is x, any point within the space. You check whether this point is within the feasible space or not. If I just add it, is it greater than 4? It is coming exactly equal to 4. All right. Let us see which direction is the, if I ask you, if I start my journey from here, which direction will be the descent direction for me, because the problem is of minimization time. What you will do? You will find out that you will say S is a direction. S direction means what? You have two variables here. Then I will say this direction will have two components, S1 and S2 again. S1 is related to x1 and S2 is related to x2. All right. Then what is the descent direction? Descent direction would be St grad f must be less than 0. And what is the feasible direction? I showed you with the geometry. St grad g must be less than 0. What we are getting from here, that S1, S2 at this point 2x1, 2x2, that is why this point is coming 2.9 and this point is coming 5.1, must be less than equal to, must be less than 0, no, not equal to 0, and this is equal to S1, S2, no involvement of x1, x2, must be less than 0. What we are getting from here? We are getting from here that descent direction is that direction where 20.9 S1 plus 5.1 S2 must be less than 0, and here the feasible direction is a minus S1 minus S2 less than 0. That is why if I ask you find out the usable direction, you will say find S such that 2.9 S1 plus 5.1 S2 must be less than 0 and minus S1 minus S2 must be less than 0. That must be the usable direction. All right. That is why for any nonlinear programming problem, if I give you the point, if you know the problem, you can find out which would be the usable direction from that point very nicely. Clear? If I just draw the graph of it, you will get another beauty here. X1, X2, X1 plus X2 greater than equal to 4. That is why if I consider this way, this is 4 0, this is 0 4 and this is a feasible space for us. All right. Now, minimization of x1 square plus x2 square. That is why my objective function is centered at 0, a center, a circle, it is moving this way. Maybe here the solution, here is the solution for you, alright, for the optimal solution. What did you see? This direction is the grad f direction, this direction is the minus grad f direction, alright. Okay. At this point, if I consider that this is the tangent at this point, then certainly, if I consider the tangent at this point this way, actually at the optimal solution, I wanted to say that descent feasible cone is empty at the optimal solution. If this is not an optimal solution, always we will get a descent feasible cone like this, okay, and this angle will help us a lot in finding it, defining the Zaudensic feasible direction method. This angle will be named as a theta angle as a push factor. Our aim is to make theta as 0, so that this feasible descent cone will be empty. That is the check for optimality later on. Okay. I will show you Zaudensic method in the next. Now, for explaining this thing, I am writing the problem once again for you. Minimization of f x subject to g x less than is equal to 0, x greater than equal to 0. Now, our target is to find out the usable direction such that St grad f must be less than 0, St grad g must be less than 0. All right. Let us introduce one artificial variable alpha such that maximum alpha is equal to maximum of St grad f and St grad g. Then this problem can be written as this way. You see, find S minimization of alpha in the screen subject to St grad f less than is equal to alpha, St grad g less than is equal to alpha. From here we can say that find S such that minimization of alpha. Why we are minimizing alpha? You see, these are all the negative values. We are getting alpha as a maximum negative values, but we want to reduce alpha, still it becomes non-positive, that is negative, that is our target. That is why we are reducing alpha, that means we are finding out minimum of alpha subject to, since alpha is max of this, that then individually this is less than equal to alpha, this is less than equal to alpha. That is why we can write it as grad f less than alpha, grad g less than alpha. What did I say? I said that S is a direction, S is a vector. If we have n dimensional decision vector, then S will have n components. That is why you must be understanding that for individual SI's, where S would be S1, S2, Sn in n dimension, individual SI will be in between -1 and 1. Okay. That is the given condition for us. That is why we can say that, we can redefine the problem as this way: minimize alpha subject to SI in between -1 and 1. One thing you see, grad f we will get from here a linear function, that I just wanted to say. This is a linear function, this is a linear function, this is a linear function. That is why if we want to have the linear programming problem, we have a constraint that if I want to apply the simplex algorithm, basic constraint in simplex algorithm is that all the decision variables must be non-negative. That is why we cannot have any decision variable as negative value. We have considered as alpha as a max of ST grad f, ST grad g. That is why alpha is negative. If I keep alpha as a minimization of minus alpha within the problem, minimization of alpha within the problem itself, then I have to declare alpha as non-positive, but simplex will not accept it, simplex algorithm. As I said, the constraints are becoming the linear constraints. That is why it cannot be, to make it positive, I am considering another variable beta. Considering beta is equal to minus alpha, then beta must be positive. If alpha is negative, beta is positive. That is why minimization of alpha will become minimization of minus alpha. And alpha, if I replace alpha with beta, it will become ST del f plus beta less than is equal to 0, ST del gj because there are j number of constraints, j can be from 1 to m number of constraints, plus beta less than is equal to 0. Now, here in Zaudenzic feasible direction method, here we can consider a factor, that is the factor is factor theta. Okay. You see, alpha is the variable, that is the constant value, S is a vector, delta f is a vector, delta g is a vector, but S is a vector, S vector is what? That is the usable direction. We are not really interested for the magnitude of that vector, we are interested about the direction of S. That is why we kept direction from -1 to 1, we have taken the normalized value of S. Okay. But we are more concerned about the magnitude of delta f, magnitude of delta g. Alright, beta is something relates to the magnitude of alpha, but you see theta j is an angle, which angle refers to the angle of descent feasible cone, that is the usable cone. What is our target? Our target is to push theta. If theta is equal to 0 means what? The constraint is tangent. That is why in other cases always theta j will be greater than 0, it cannot be less than 0. Less than 0 theta j impossible. Okay? That is why this push factor we have considered with beta only by taking theta j as greater than 0. Okay? That is why the original problem, we had original problem minimization of fx subject to gx less than is equal to 0. Now, it is becoming a problem of this kind, minimization of minus beta st delta f plus beta less than is equal to 0, st delta gj plus theta j beta less than is equal to 0, theta j, theta is again is having different components. For one constraint, for the jth constraint, the component is theta j for theta. All right. Now, for that is why individual theta j must be greater than equal to 0. At the optimal stage, for one constraint theta j is equal to 0, for other constraints it may not be in that way. This is the push factor we are considering. But again you say this is, if we consider as a linear programming problem, the problem is again here is that we cannot take S as a negative value. Though we have considered S as a magnitude of the vector for the usable direction, and that is why we took the normalized value from -1 to 1, but once it is coming as a linear programming problem, all the decision variables must be positive. Then let us have certain mechanism so that this negative variable will be converted to positive variable. That is why we will consider that one factor T I, that is equal to S I minus 1. So that S I is becoming from -1 to 1, then T I will be from 0 to 2. That is the beauty of this method. Okay. Once we can have it, then the whole problem can be rewritten as this one, that find out the direction, this is the component of S, such that ST delta G plus theta j, that is the push factor, into beta less than is equal to 0, and this is less than is equal to 0, and T I in between 0 to 2 and beta greater than 0. How it is being expanded, that you will get it if you just take the first order derivative of the constraint with respect to decision variable, because we have that factor with us. And if I just tell you, I will tell you more about the Zaudensic feasible direction method. With example, I show you how it is being expanded in this manner in the next class, but before to that I will tell you the algorithm once. Take the initial feasible point x1, that is of your own choice. If your choice is good enough, then your number of iterations will be less. Now find out f and g at that point, then if g I is less than 0, then must be in the interior point. Now find out the feasible direction as grad f x I at that point, that is the feasible direction. So that S grad g must be less than 0, that is why that is the direction, feasible direction, and g j you have to consider. Then you construct this problem, consider T I in such a way that it will become from 0 to 2, take beta, beta corresponds to minus alpha, we want to reduce alpha, that is why our target to make alpha as 0, that is why in other hand we are making beta as 0. Okay. That is why our stopping criteria would be, if the beta value is very small, we can conclude that the optimal solution is that one. Okay, that is the thing for you. Now this is the step 5. Once we get SI, we will get the length, suitable length we will find out, and this is the check for optimality, and we will do the solution for this. We will repeat again and again. Now I will explain more about this algorithm, the calculation part of the feasible direction method along with the example in the next class. Thank you very much for today.